4.5, Isosceles and Equilateral Triangles. Okay, in this lesson, we're going to learn about the properties of isosceles and equilateral triangles. Now, I promised you that we would be getting more ways to prove sides and angles congruent so that we could do more with our triangles, and this is one of our first steps of doing that. So, isosceles triangles are really common. They're very useful. A triangle is one of the strongest structures, the way it distributes loads. And so these are everywhere. You see them in bridges and buildings and supporting structures, things like that. So this is good stuff to know. Now, here is some vocabulary for us. What's the definition of an isosceles triangle? Right? Do you know that? Definition of isosceles triangle is a triangle with two congruent sides. I bet you knew that. So let's do some vocabulary here. The congruent sides of our isosceles triangle are called the legs. So this side and this side are your congruent sides, and those are your legs. Now, the two congruent legs form the vertex angle up here. Your third side is called the base. So we have the base down here. And then the two angles that the base is included between the other two angles, which we call base angles. This angle here and this angle here are your base angles. So it's really important to know which sides we're talking about when we're discussing triangles. It's important for our theorems. So there's our vocabulary. Let's look at our first theorem here. It's called the isosceles triangle theorem. And we can shorten this one to isosceles triangle theorem. And guess what it deals with? It says, if you have an isosceles triangle, right, see our diagram here, we've got our two congruent sides. If two sides of a triangle are congruent, then what's going to happen? Then the angles opposite those sides are also congruent. So what we end up with here is if you have an isosceles triangle, then you know that your base angles, these are your base angles are going to be congruent. So now, you see, we've got some congruent angles here. The proof of this theorem is really pretty straightforward. So we say, well, if we have an isosceles triangle, right, so I've got that, got two congruent sides, and we are going to draw an auxiliary line to help us with this, and we're allowed to draw a line through any 2 points. There exists a line, right? You can draw one and only one line. I'm going to draw a line through my vertex angle down to the base, and what that's going to do is I'm going to draw an angle that bisects my vertex angle. So what I'm going to do here is I drew specifically the bisector of the vertex angle. And then I'm sure you can see reflexive property. So this is definition of angle bisector. These sides are given. We've used our reflexive property of congruence. And we now have two triangles that are congruent by side angle side. And once our triangles are congruent, what can we do with that? Well, we know that all other corresponding parts are congruent. So if I write my congruence statement, I can say that triangle YXB is congruent to triangle, and what's the other angle over here? ZXB. And look at angle Y and angle Z. They are in the same position. So I get to say that these two angles are congruent because I know that corresponding parts of congruent triangles are congruent. So that's how we do this proof. Very simple, very straightforward. Once I have my triangles congruent, all other parts are congruent and corresponding parts. So we can do that. All right, that's a nice little proof there. Now, our next theorem is called the converse. And what does a converse mean? It means we switch our if-then statement. So the converse of the isosceles triangle theorem, what did our isosceles triangle theorem say? Let's look at it. It said if we have an isosceles triangle, if two sides of the triangle are congruent, then the base angles, the angles opposite those sides, are congruent. So what's going to be the opposite of that? That's right. We start this one if two angles of your triangle are congruent. So we have these here. Then the sides opposite of those angles are also congruent. So we're looking at marking that. And you are allowed to mark those sides. So now we have another way of proving sides congruent, which is where we were really lacking before. We now have two sides that are congruent. So the two angles, these are our base angles, and then the sides opposite are going to be our legs. All right, so if you have two congruent angles, then the sides opposite those angles are going to be congruent. You automatically can mark that, justifying with the converse of the isosceles triangle theorem. So let's look at this in terms of problem solving. We want to know, is segment AB congruent to segment CB? So I'm looking at my diagram here, and I am dealing with just the big triangle. So I am going to redraw ABC, and what do I have given to me? Well, I know that angle A and angle C are congruent. So can I say that segment AB is congruent to segment CB? Absolutely. How come? That's the converse of the isosceles triangle theorem. Right? These two angles are congruent, so my two sides are congruent as well. Okay, what's next? Is angle A congruent to angle DEA? So there's angle A, where's angle DEA? We're talking about this angle right here. So now I'm talking about the small triangle in there. So I'm going to redraw and talk about ADE, and I am going to mark anything that I have here. I have this, and I have this, and I have this. So I want to know, can I say that this angle here is congruent to this angle here? Why, yes, I can. I can mark that one congruent to this one. That's just the isosceles triangle theorem. My two legs are congruent, so my base angles are congruent. All right, again, separating apart, redrawing so that you can see only what you're talking about is really going to be helpful. And remember, if it's not marked, if you don't have a theorem or postulate or definition for it, no matter how much you want it to be true, won't make it true. So be careful and pause the video and try the next problem. Okay, we were asked to do a couple of different things here. The first question was, is angle WVS congruent to angle S? So on this part, you should have said, well, we're working with this little triangle over here on the right. And so I redrew that, and we were given that we had two congruent sides. So yes, I can mark my two angles congruent by the isosceles triangle theorem. So that let me mark this and this congruent. And then we're asked, is segment TR congruent to segment TS? Well, now we're working with the big triangle, so I redrew the big triangle. And from the previous problem, we know that angle WVS is congruent to angle S. We just marked that. And from the diagram, we know that angle R here is congruent to angle WVS. So our transitive property lets us say that angle R is congruent to angle S, which then lets us mark our sides congruent by the converse of the isosceles triangle theorem. We have two congruent angles, so our sides can be congruent. And then our third problem here says, can you conclude that triangle RUV is isosceles? So that's the kind of medium-sized triangle here on the left. So I redrew that, and as much as you wanted to make these bottom two angles congruent, you cannot. They are not marked. There is no way to make them congruent. They're not vertical angles. You may want to look at them and go, oh, vertical angles, but they are not. Those are not intersecting lines. There are no congruent sides and no congruent angles. We cannot make that an isosceles triangle. Hopefully you saw that. All right. Our next theorem, this is what I call the awesome theorem, but we don't get to call it that. Sorry. This says if a line bisects the vertex angle of an isosceles triangle. So we know that we have an isosceles triangle. So those two sides are congruent. And this line is an angle bisector. So these two angles are congruent. Now we've seen this before. We just used it to prove our theorem. Right? So if a line, and we're talking about this line right here, if a line does all of this, it bisects the vertex angle of an isosceles triangle, so a lot of requirements here, then that line, we're talking about the line, is a perpendicular bisector of the base. Okay, so we have an isosceles triangle, and the line is the bisector of the vertex angle. Then the line is perpendicular to the base and bisects the base. Remember, perpendicular and bisect are two separate things. So it's perpendicular to the base and it bisects the base. I'll erase the is, it doesn't go with bisect. We're talking about that line that bisects the vertex angle. So don't forget that. Now, this is a really awesome theorem. It gives us lots of information. Let's look at how we use this. We are given a triangle here, and I see an isosceles triangle, and I might draw my isosceles triangle a little bigger so that I can see better what's going on. There's A, B, C, and I draw it upright because that's kind of how we like to look at our. And so I know it's an isosceles triangle. What do I know about isosceles triangles? Well, I know that these angles are congruent, right? Isosceles triangle theorem. And what else are we given here? We are given that these two angles are congruent. That's just a given. Do you see the angle bisector of that vertex angle? Immediately, I know that that is a right angle, and those two segments are congruent because of our awesome theorem. This is labeled x degrees. This is labeled 54 degrees. So what can I do now? Well, I can label this 54 degrees, and this x degrees, and this 90 degrees, and this 90 degrees. And now it's easy enough to find x using the triangle angle sum theorem. 54 plus 90 plus x is 180, so I can find x. Now the next question says, what if the measure of angle A was 27 instead of 54? Well, then we would just do 27 plus 90 plus x equals 180. That's 117. So I subtract 117 from both sides, and x is 63 degrees. So I won't make you stop and do that one. It's really straightforward. You're going to want to forget about this theorem, especially since it doesn't have a name and you have to write it out. But it really is an awesome theorem. Lets us do a lot of things. All right. Two more theorems here, but not really. Okay. We only have one real new idea here, and that's isosceles triangles. Isosceles triangles have congruent base angles. The converse says if your base angles are congruent, then you have an isosceles triangle. Our awesome theorem says that if you have an isosceles triangle and you bisect the vertex angle, you have a perpendicular bisector of the base, which is just way too cool. Lets us do lots and lots of things. A corollary is a theorem that is proved using another theorem. This is an extension, or a special case. So a corollary, and we are not going to let them write this, corollary to the isosceles triangle theorem, and the corollary to the converse of the isosceles triangle theorem. Scratch those out, make it all go away. All right, our corollary here to the isosceles triangle theorem, this is an extension of the isosceles triangle theorem, a special case of the isosceles triangle theorem, says if your triangle is equilateral. What does equilateral mean? That means equal sides. Then the triangle is equiangular, so equal angles. So if our requirement here is equal sides. Now, is this an isosceles triangle? What's the definition of an isosceles triangle? Well, definition of an isosceles triangle is a triangle with two congruent sides. This meets that requirement. What do we get to do if we have an isosceles triangle? Well, we get to mark our base angles congruent. Now think about this. If we rotate this triangle around, then our other two sides are legs, and my other angle becomes a base angle. So all of these can be legs, and all of them can be base angles, and that is how we can say that all of these angles are congruent. So I want you to think about this for a minute. you're given an isosceles or an equilateral triangle. And you go, hey, guess what? I can automatically mark all of these angles congruent. And now I'm going to label this one x degrees. Well, how much does the next one measure? X degrees. How much does the next one measure? X degrees. If we use the triangle angle sum theorem, didn't think we were getting away from that one, did you? Then I can say x plus x plus x equals 180. So 3x equals 180. Divide both sides by 3, and x equals 60 degrees. This is true for every equilateral triangle. So you run into an equilateral triangle and say, I need that angle measure. Guess what? You have it. These are just as special as right angles. You know right angles measure 90 degrees. Equilateral triangles, they're equiangular, and their angles always measure 60 degrees. It's just the way it is. All right, let's look at the corollary to the converse of the isosceles triangle theorem. Converse means we just flip it around, and guess what? Yep, if your triangle is equiangular, so equal angles, then your triangle is equilateral, equal sides. So if we have equal angles, then we can automatically go and mark all of our sides congruent. So very simple. Let's look at the example here. How does this help us? Let's find something that'll write on these colors. We want to know what the measures of angle A, angle B, and angle ADC are in our picture here. Well, as soon as I look at this, I see equilateral triangles. And I also see congruent equilateral triangles. Look at our first one here, right? And then it shares a side and all the other sides are congruent. And then it shares a side and all the other sides are congruent. So the first thing I can do is I can say, well, I know all three of those angles are congruent by the corollary to the isosceles triangle theorem. I have an equilateral triangle. It is also equiangular. Okay, and then I look here and I have the same equilateral triangle, so I can also mark this angle, and this angle congruent. And then the same holds true for this triangle over here. So they are all the same triangle. And then I want to know what's the measure of angle A. Well, it's an angle in an equilateral triangle, so it has to measure 60 degrees. And so does this angle. And what else we asked? Angle B. Angle B has to measure 60 degrees. And so does this angle, and this angle, and this angle, and this angle, and this angle. And this angle up here measures 60 degrees. So when we are asked for angle ADC, that angle right there, I know that it's 60 plus 60, and I get 120. So the measure of angle A and B are 60 degrees, and the measure of angle ADC is 120 degrees. So again, drawing, marking, labeling, everything is extremely important. And we now have some very fun theorems that will let us have more congruent angles, more congruent sides. We can do more with our triangles. Isosceles triangles, 2 congruent legs, 2 congruent base angles. Converse, congruent base angles, congruent sides. Equilateral triangles, 3 congruent sides, 3 congruent angles. The converse, 3 congruent angles, 3 congruent sides. And don't forget our awesome theorem. If you've got an isosceles triangle and the vertex angle is bisected, then very special things happen. You've got a perpendicular bisector to the base. So that was fun. I hope you enjoy isosceles and equilateral triangles.